Okay, we're going to talk about continuity. It just means when a function is continuous. So a function is continuous. So I'll write this down. So a function is continuous if you can draw it without picking up your pencil. Okay, that's how you know if a function is continuous. So for an example of that would be a parabola. So if I were to just draw a parabola, I can without picking up my pencil. But if I were to draw, this would be my non-example, some type of piecewise function like this, and then I pick up my pencil, continue it over there, that would not be continuous. Okay, so there's a technical definition that we use whenever we have to prove that something is continuous, and it's right here. A function is said to be continuous at x equals c. So that c just means a number, like 2, for instance, provided the conditions are satisfied. That function is defined at that c value, so like f of 2 is defined, or the limit as x approaches c of f of x exists, which is the same thing as, well, x approaches 2 exists, and then these two values, pretty much 1 and 2, match up. There is kind of a shortcut to that, so if the limit as x approaches c from the left equals the limit as x approaches c from the right equals f of c. And this really takes care of all three of these things, because if that underlying part works, then that checks for part 2, okay? If f of c is a number that we can put in there, that checks off part 1, and saying that they are equal actually checks off that last part right there. So a lot of times I'll just go through and just show that statement right there. Okay, let's move on to continuity on an interval. This is definitely going to be a lot less work if we're asked to find the continuity on an interval, because we can just assume continuity unless we find something that is discontinuous. It might sound a little confusing, but when I do examples, it won't be. So pretty much a function is continuous on an interval if it's continuous between a and b. It doesn't have to be if you notice, it's not touching a and b, the interval. All right, so it's just from a to b. It doesn't have to equal a or equal b. It's continuous on the right side of it, so it's continuous going to the right. So if I have a function like from here to here, this is a and this is b. All right, so I'm continuous going that way, and I'm continuous going that way, because that last one mentions the left. So that one's a little more technical. We don't know about that technical one. The one I'm more worried about is the one I did up in blue. And then these are discontinuity types. So removable is just when you have a hole. So I'll draw an example. Let's do green. So if I just have like a hole in the middle of a function, that is removable. Okay? So a jump is when the function goes from one thing to another. So you can kind of see there, it jumps from that left part to that right part. And then infinite, that's when you have a vertical asymptote. So like for instance, one of those, that's an infinite. So removable, that's the same thing as a hole, by the way. All right, jump is usually going to be piecewise functions. Not all piecewise functions, but if they're not continuous and it's a piecewise function, it's a good chance it's a jump. And then infinite is when you have vertical asymptote. Okay, and we'll kind of get into that as we get through these examples. So example 1, determine whether the function is continuous at x equals 2 and x equals 5. So I'll do there's two parts to this question. So you look here, we have a piecewise function, and it breaks off at 2, and it breaks off at 5. Okay, so what I do need to do is step 1. So this is for x equals 2. So for step 1, f of 2, does that exist? Well, yeah, because it's got this equal to right there. So that does exist. So it exists. If that didn't have that equal to part, then 1 fails. And once 1 fails, you're good. You don't need to do anything else. And we got to show that now step 2, I'm getting these numbers from here, by the way. Show that the limit exists. So in order to show that the limit exists, the limit x approaches 2 from the left has to equal the limit as x approaches 2 from the right. Well, does it? So on the left, this is the left-hand side right here, and here's the right. So the left, if I plug in a 2, I'm going to get 2 times 2 plus 3, which is 7. And the right-hand part is just, well, 7. So yes, so the limit as x approaches 2, f of x exists. Okay? And then step 3, well, what is f of 2? F of 2 is 7, which equals the limit as x approaches 2, which is also 7. So therefore, f of x is continuous at x equals 2. Okay, so lots of fancy mumbo jumbo stuff there for continuity. If you can just tell right off the bat something's not continuous, you don't need to go through all these steps. You can just pick one out and go, oh, well, that doesn't work. But I'll go through this anyway. So for step 1, f of 5, there is a value at 5, and it's 7. So that exists. Okay, it does equal. This is where we're actually start to have trouble, though. So the limit as x approaches 5 from the left of f of x is equal to 7. What about from the right? So this is the left, this is the right. I know I'm kind of skipping ahead a little bit right here. So again, we're looking at 5, so the left part is 7. The right part is when we plug in that 5 into that bottom one, so it's going to be 5 squared minus 1, which is 24. So the limit, x approaches 5 of f of x does not exist. So therefore, f of x is not continuous at x equals 5. Okay, you didn't need to show 1. If you just knew it was not going to be continuous, you could have just showed step 2 and then been golden. So whenever we need to determine something is continuous, you have to show all these steps. And by the way, real quick, this is going to be a removable discontinuity. Okay, it's removable. Sorry, not removable. It is not removable. It's a jump. Because whenever the limit doesn't exist from the right and the left, so if 2 fails, it is a jump. Because the limit on the right and left are different. Okay? All right, determine whether the following is continuous at 3. Here we go. So we can do step 1, which is f of 3. Does f of 3 exist? Well, go ahead and plug in a 3 and, well, it does not exist. Because if we plug in a 3, we're going to get 3 plus 2 over 3 minus 3, which is 5 over 0, which does not exist. Okay? So that f of x, we're at y. So y is not continuous at x equals 3. And this is actually going to be, since the bottom equals 0, that's going to be an infinite discontinuity. It didn't ask us for which ones were which. I'm just trying to go through with you how you can figure it out algebraically. If you get a picture, it's very, very easy to tell. You don't have to do any of this work for a picture. If you're just given a random graph, you can just go ahead and say it's not continuous. If you have to trace it, pick up your pencil, it's not continuous. All right, and then the last two questions. Identify the interval in which the function is continuous and the discontinuity type, if applicable. So this one, we don't need to prove that it's continuous, so we can just skip all those steps. What we want to do is find our discontinuity. Okay? So we need to look for holes and vertical asymptotes. Since there's no piecewise functions, I'll just say jumps. There's not in any of these examples. This is going to be on the domain. So look for holes, vertical asymptotes, and jumps. Okay, so for this one right here, for A, do that in purple here. So for A, looking at this function right here, we can actually start factoring it to simplify it a little bit. So the top is going to factor as x plus 3, x plus 1. The bottom is going to factor as x minus 1, x plus 1. If you notice, x plus 1's cancel out and you get x plus 3 over x minus 1. So this is actually going to give us a hole at x equals negative 1. Okay, I set whatever you canceled equal to 0. So we get a hole at x equals negative 1. And looking at this function right here, to find the vertical asymptote, you look at the bottom. Okay, so you set the bottom equal to 0, so we're going to have a vertical asymptote at x equals 1. So those are the only places that it's discontinuous. So it's going to be continuous on, well, from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. Okay? These are the intervals in which we are continuous, from negative infinity to negative 1, negative 1 to 1, 1 to infinity. Let's say the types of discontinuity. So at x equals negative 1, we have a hole, so it's going to be removable. And we're going to be infinite since it's the vertical asymptote at x equals 1. Okay? And then for B, this is our last example we have here. By the way, I'll do this in different colors. So we're do it in blue. Not what I wanted. Okay. This is actually a semicircle. How do I know that? Well, because x squared plus y squared equals the radius squared, in this case 16. If you were to solve for y, you would actually get this right here. It's just becoming more and more familiar with these functions. So think about that. It's a semicircle. You can just the top because it's plus or minus. Just look at that. Is that continuous? I don't want to sound like a great picture. Let me draw that again. Do I pick up my pencil? No, so it's actually going to be continuous all the way through, okay? Now, is it continuous from negative infinity to infinity? Well, that's not on the domain. The domain lies in here. We can't have a radical ever that is less than 0. So we have to be 16 minus x squared has to be bigger than 0. All right, so just think about that real quick. What numbers can we have? Well, does 0 work? Yeah. Does 1 work? Yes. 2? Yes. 3? Yes. I can equal it, by the way. 4? Yes, it actually works. 5 does not work. So just got to think about it a little bit. This is actually going to be continuous from -4 to 4. Because when I do this work over here, I'm going to get 4 minus x plus 4. When is that bigger than 0? And then that's when we make our little sign chart. If you remember that from earlier in the year. So we have critical value at 4, critical value at -4, and we can go ahead and make our sign chart here. So at -4 and 4, it's going to go, plug in a negative number, you're going to get negative. Plug in a 0, and you're going to get positive. Plug in a 5, you're going to get negative. And this is only true here. So this is our domain, and it's continuous in that entire domain. Okay, and that's all.